Greetings, physical science students. Welcome to the end of Unit 1 in our chemistry quarter. So far, we have covered things like the history of the atom, periodic trends, isotopes, ions, all kinds of stuff. And this video is an attempt to run through those real quick so that you can get a brief overview of what you can expect to see on the test. So without further ado, let's get into it. All right, so here I have the breakdown. Now, again, we also talked about the electron wave model, which is very similar to the electron cloud model, other than the fact that it depicts the electrons moving in waves rather than in clouds like this one does. Okay, but I just want to go through and kind of summarize what we know about each one. So let's start with the billiard ball model. Remember, that's the oldest one. Okay, this is the one where basically there is nothing present. That is the very first one where they basically just said that everything, let me see if I can write this, everything is made up of tiny particles. Okay, and that's all they said. They didn't know anything about charges, anything about really anything. They just simply stated as you get smaller and smaller, things are made up of these tiny particles or billiard balls as they called them. And that's basically it. Okay, now, then we get to the plum pudding model. This does not have protons yet, okay, although all of this red material in here, okay, that is what we call a positive material. So the person that came up with the plum pudding model basically said that there were electrons, that's the blue dots here, okay, a bunch of blue dots scattered throughout positive material. So electrons, okay, inside a positive material. Okay, that's all the plum pudding model was. The reason that we had the plum pudding model was basically because we figured out that there must be some kind of negative charges in there somewhere because of their ability to repel things. And then lastly, we have the Bohr model, or not lastly, but next we have the Bohr model. This is also called the solar system model because, as you can tell, in the center there's one center, and that's what we call the nucleus. Okay, and then we have the electrons orbiting it. Okay, so remember, in the nucleus is where the protons and the neutrons are. Neutrons. Okay, and then on the outside we have our electrons. Okay, so this model, remember that we also draw pictures of this model a lot just to kind of see the different levels of the electrons and that sort of thing. Okay, but this is the one that has to do with all the orbits of electrons. Okay, so all the electrons are orbiting the positive nucleus. And then lastly, the electron cloud also has protons because it has its nucleus right there in the center. And then it also does have electrons. Now, the thing is that you won't be able to see the electrons in the actual model itself. Okay, what they do is they give you these little clouds and they tell you the electrons are somewhere in those clouds. Okay, somewhere in those clouds. Okay, so that's where the electrons are. I'll put electrons up here. Okay, so they use the same premise as the Bohr model in that it has a positive nucleus with protons and neutrons, and then instead of the electrons going in perfect orbits, they actually appear in these clouds, and they actually move so fast that we don't know exactly where they are. Now, in between these two models, remember that there's the wave model, electron wave, and it's exactly the same as the cloud one, except they move in waves rather than in perfect orbits like the Bohr model. Okay, so you can imagine it's kind of like the Bohr model, except these lines are all waved because they travel in waves instead. Okay, and that's pretty much it for models of the atom. All you need to know are these things. Okay, how they look, Okay, kind of a description of what they mean. Okay, and then definitely know the order from billiard ball to plum pudding to Bohr model to wave, and then finally we use the cloud model currently. Okay, moving on, we started talking about atoms and how the periodic table looks and what numbers tell us what. Okay, so remember some vocab here. We have atomic number. That is the number of protons in the nucleus of an atom. It is the defining characteristic. It is always at the top of your little squares on your periodic table. This is telling me that xenon has 54 protons. Okay, if I knock that down to 53, I no longer have xenon. I have a different element. Okay, so the defining characteristic is always the number of protons in the nucleus. Next up, we have the mass number. This is the number of protons plus the number of neutrons in the nucleus of an atom. It actually does not show up on this. This has more to do with isotopes. So for example, if I said, xenon 131, then that would tell me that the mass number is 131 and that there are 131 protons and neutrons in its nucleus. Okay, and if I know that automatically there are 54 protons, I can subtract and figure out how many neutrons there are. Okay, the average atomic mass shows up right here at the bottom. Okay, this takes into account the percent abundance and mass numbers of all isotopes of the given element. This one right here is telling me that xenon 131 is the most common isotope of xenon because this number is closest to 131. Okay, and that works for all of them. So carbon will have one that says this, and I think it's like 12.022 or something like that. That tells me that carbon 12, there's an R in there, carbon 12 is the most common isotope of carbon. Which leads me to my next definition of isotope. This is an atom of the same element with different numbers of neutrons. So for example, xenon 131 might be the most common, but I can go out there and I can find xenon 132, and all that means is I added one more neutron to my nucleus. Okay, so if I have 54 little protons in here, just imagine there's a bunch of circles in there. Okay, and then whatever 131 minus 54 is, off the top of my head, I don't know. 131 minus 54. If you imagine, that's going to be 77 neutrons. Okay, 132 is going to have 78 neutrons. Okay, and so then that'll be added to my nucleus, and I'll have a different isotope of xenon. Okay. Moving on, we also talked about the locations of different types of groups inside our periodic table. Okay, so a couple things. First of all, the noble gases are over here on the far right. Okay, these things do not bond to anything. That's why they're called the noble gases. Okay, they're called noble because basically they don't associate themselves with any of the other elements in this one. These ones have full outer shells when it comes to electrons, okay, which is why they don't bond to anything. In the next unit, when we talk about chemical bonding, we'll talk about how things share electrons or give electrons and that sort of thing. The next one, right next to it, these ones are called the halogens. I guess I should label these the noble gases. Okay, noble gases. Hey, let's see. So I have noble gases gone. I've got halogens gone. The transition metals are all of these ones right here. Okay, transition metals. Okay, these are the ones that kind of work a little bit more weird in the periodic table, meaning that a lot of these groups, so for example the noble gases, they have all the same properties. They have full outer shells, all that stuff. They kind of all work the same. Halogens, same thing. They actually need one more electron in their outer shell, which we'll talk about again when we talk about bonding. And then transition metals, they can kind of fluctuate between needing electrons and not needing electrons. They move back and forth, and they kind of react a little bit differently. As we move left in the group 2, we call this group 2. This is group 1. Technically 3, 4, 5, 6, 7, and 8. And again, those transition metals are kind of skipped over because of their different properties. But either way, in second group, we have the alkaline earth metals. Alkaline earth metals. Okay, and then lastly, we have the alkali metals. Okay, and all of these have different properties, which we get a little bit more into in Unit 2 when we talk about chemical bonding. One thing I do want to point out is that hydrogen is actually not part of the alkali metals. It's not a metal at all. Because of where it is in the periodic table, it kind of just fits into that group without having the same characteristics as the same ones. And I believe that covers all of the ones I had. Okay, so make sure that you know where they're located. Alkali metals are the first group, alkaline earth metals are the second group, transition metals go across the middle, and then on the ends we have halogens, and then we have our noble gases on the far right. All right, that leads me into talking about ions and cations. Negatively charged ions are called anions. These are the ones that want electrons, and these ones are going to be the ones that are on this side of the periodic table. Notice again that noble gases, I'm not going to circle them because they don't actually want any electrons, and they also don't want to give electrons because they're full and they are stable just the way they are. Okay, so things on this left side, they want electrons. Okay, mostly because of their outer shells. So for example, this one, okay, what we need is one electron. So we need one negative in order to become full. And again, when we talk more about bonding and stuff, this will make even more sense. Really what you need to know right now is that anions are more on the left or more on the right side, and cations are more on the left side. Okay, these are the ones that really just want to give away their electrons to become neutral so that they can make a stable element and have full outer shells. Okay, that also leads me to the and that leads me to my next thing that I forgot to mention and that we talked about, and that is the duet and octet rules. Okay, remember the duet rule means that the first level of electrons wants to have 2 electrons. Okay, and that really only pertains to as far as being full, hydrogen and helium. So hydrogen has 1 electron in that first level, and helium has 2. Because helium has 2, that makes that level full, and why it doesn't want any more electrons. Everything else needs 8. Okay, so all other levels need 8 to be full. Okay, and so when we draw our Bohr models and our Lewis dot structures, we base it off of having 8 in our outer shell. Okay, and so if you imagine lithium, for example, lithium has 3 electrons because that's what its atomic number is, because you have to have equal amounts of protons and neutrons. And so it has, let's say the nucleus is right there. It's got 1, 2 in its first shell, and then 1 in its next shell. Always trying to get to 8 after that. All right, so next up we talked about periodic trends. And here I have a summary of the ones that we talked about and how they increase across the periodic table. So let's talk about atomic radius. Okay, we said that atomic radius increases as you go down and as you go to the left. So if I look at a few of my elements, let's look at these three. Oxygen, out of these three, is going to be the smallest in terms of atomic radius. Cobalt is going to be the biggest because it is the farthest down and to the left. And then I believe that is Serenium or something like that. And that one is going to be in the middle. Now, the good thing is that these three, they all have this same trend. They increase as they go right and up. Okay, so if I look at those same three elements, okay, the electron affinity increases as I go up and to the right. The electronegativity and the ionization energy all do the same thing. So that means oxygen has the highest electron affinity, electronegativity, and the highest ionization energy, which also means that cobalt has the lowest, and that again, Serenium is right there in the middle. Okay, as far as metallic characteristics go, okay, it goes down and to the left. Okay, so down and to the left. Okay, and that just tells me that cobalt is going to have more metallic features than oxygen. Okay, oxygen is going to have a lot less. They're going to have more non-metallic characteristics, and that's just their position, and that goes this way for metallic, that way for non-metallic. All right, I wanted to also go into exactly why periodic trends work the way that they do, and just do a kind of a better job at explaining to you why atomic radius has the trend that it has, and so on and so forth. So let's start with atomic radius. Okay, and so since we know that it increases as we go down and as we go to the left, basically we know that francium has the highest atomic radius out of all of the elements. And the reason that is because of its placement on the periodic table. So one real quick, I'm going to number our groups. S7 and 8, and then I'm going to number the periods. Okay, so the groups are the columns, and then I'm going to number the periods, and really I care about it being the 7th one. Okay, but either way, francium is in the first group and the 7th period. The periods, so this 7 means that there are 7 levels of electrons in the atom. Okay. This 1 means that there is one, one valence electron. Okay, so one outer electron. So if you imagine on our Bohr models, let's say that's the nucleus, that's one level, 2, 3, 4, 5, 6, 7. Okay, I didn't really have room to draw all 7 there, but anyway, so francium has 7 levels. Okay, everything in the 7th period has 7 levels, and it also only has 1 in its outer shell. Okay, so if you imagine the only thing keeping this electron in this atom is the positive pull of this nucleus. Now, because there's only 1, okay, that pull is very, very weak. Okay, so it's all the way out here, and it's just swinging around. Okay, and it's really, really loosely bound. So it's making the atomic radius really, really big because it's going out and around, and it's just barely attractive, almost basically falling off on its own. Okay, and that's why the atomic radius increases as you go down and as you go to the left. And that's because you're increasing the number of levels of electrons and decreasing the number of electrons in those levels. Okay, so for example, potassium, okay, it has 4 levels and only 1 in its outer level, so it's going to be pretty wide as well. Not as wide as francium, obviously, because it's below it. Okay, the other three that I want to talk about, these three, also have to do with those valence electrons. It's probably the most important aspect of elements in determining their traits. Okay, so the number of valence electrons greatly changes these three things. Okay, the strength of the nucleus attraction. Notice that these three do the exact opposite as atomic radius does. So it increases as it goes up and to the right. Okay, so for example, fluorine has a relatively high all three of these: electron affinity, electronegativity, and ionization energy. And so the reason, again, is because it's in the 7th group. It has 7 valence electrons. Okay, 7 valence electrons. Again, trying to get to 8 means that the energy required to remove a valence electron is really high, because when we have 7, we really want to gain one more to get to 8. Remember, that's our octet rule. Okay, so it's not just going to give up an electron easily. Okay, that's what makes the energy increase as you go up and also as you go to the right. Whereas francium, like I told you, this one electron way out here is really weakly bound. It will give away its electron with very little energy and basically give it away to whoever wants it. Okay, electronegativity as far as tendency to attract more electrons. This group in general loves to attract electrons because it really wants to get to 8 valence electrons. So this whole group has 7, so their tendency to attract more electrons is really high. Okay, same thing with the strength of the nucleus attraction. Okay, as I get more levels, I get less proton attraction from the nucleus, which is why the top right has the strongest nucleus attraction, because it only has 1 level. It's got 2 protons in its nucleus, making it really strong pull for that helium atom. Hey, and I hope that helped to explain kind of why these things work the way that they do. And so when it comes up on the test, that you'll know exactly what to do. Okay, next we are going to talk about isotope and ion tables. Okay, this is the math portion of this. This top one is the one that deals with isotopes. Isotopes, I can spell. 1 second. And this one is ions. You can tell that based on the numbers right here and right here. Those are ions. The symbols for these ones, notice that they're just regular and they don't have any pluses or minuses. So that tells me that this is going to be about isotopes. All right, so let's start with the first line. So we have carbon. Okay, so I'm going to write carbon here. And then the symbol is C. The atomic number is 6 and the mass number is 14. Remember that you need to write those up here, 14 and 6. The atomic number is the same as the number of protons, so that is going to be 6 right there. And because this is an isotope, protons is always going to equal electrons. The only time it's different is when we have ions. Okay, and so that'll be on the other table. So for isotopes, electrons equal protons. Equals. Okay. The way you get neutrons is that this number plus this number should equal your mass number. Okay, so what plus 6 is 14? That number is going to be 8. All right, moving on. Next one down, protons is 19, so I know the atomic number is 19, and I know the electrons is 19. Excuse me. Okay, the other thing I know is that, again, this number plus this number equals this number. So I have 20 plus 19, and that should be 39. Okay, and then we have to look up what atomic number 19 is, and I have it here on my phone, and it is potassium, which symbol is K, and we put the mass number on top, and then we put the atomic number on bottom, and I'll write out potassium right here. Perfect. For whatever reason, I have an extra row in here that doesn't have any numbers or anything. So instead, I'm going to move on to zinc, which is the 30th element. Let's see. If the atomic number is 30, then the protons is 30 and the electrons is 30. Remember again that this number plus this number equals this number, and that is 30 plus 34 is 64. I go back to my symbol, I make sure that 64 is on top. I make sure that my atomic number 30 is on bottom, and then I am done with that table. All right. So now we're going to move on to ions, and the very first one I have there looks like an iodine ion with the I to the -1. So I'm going to put iodine here. Okay, the atomic number for ion or iodine when you look it up is 53. You could also tell that from the protons. Now make sure for ions that you don't just copy protons and electrons. They are different now. Okay, because this has a -1 charge, I know that I gained an electron, which tells me that I now have actually 54 electrons. Okay, so gaining a negative would mean that I gain an electron, so taking it from 53 up to 54. And then again, I have this number plus this number equals this number. And so I do the same thing, 120, whatever 127 minus 53 is, which would be 74. Perfect. Moving on to the next one. Gotta open my phone again. Atomic number 35 is what we're looking for, which happens to be bromine. Okay, and that is a Br. Okay, 35 atomic number means 35 protons. Okay, and then I need to compare these again. So 35 and 36, I have gained 1 electron, which means that I have a -1 charge. And then I do neutrons the exact same way. This plus this equals that. So whatever 79 minus 35 is, and I got 44. Okay, so 44 neutrons for that one. All right, moving on to the next one. I've got 7 protons, so I know my atomic number must be 7. The 7th element is nitrogen. Nitrogen. Okay. Let's see, the mass number is neutrons plus protons, so that is 14 right here. Notice that I have 10 electrons. Okay, that is a gain of 3 electrons from originally having 7, because you know originally I have 7 and 7 to make it neutral. So that would be a -3 charge on that one. And then I'm done with nitrogen there. That has everything filled out. Last one is aluminum, Al. So Aluminum. Okay, aluminum. The atomic number for aluminum is 13, telling me that there are 13 protons. And if I do neutrons plus protons equals mass number, whoops, equals is what that's supposed to say. Equals, and that's a plus. And I know that 14 plus 13 is 27. So that is how you do your isotope and ion tables. Okay, on your test I will ask you about certain ions or about certain isotopes, and you'll have to do some calculations in order to solve them, just like on your quiz. So make sure that you are prepared for that. If none of this makes sense, make sure that you reach out or come to office hours and we will go over them again. All right, so next up we have Bohr models and Lewis dot structures. Okay, so again, these are going to be drawing ones. So let's just get into it. We have a neutral phosphorus atom that we need to make. And so I'm going to start with phosphorus here. If you imagine for our Bohr model, the first level can only have 2 electrons. Okay, that's the duet rule again. Next level, octet rule, I can have 8. So 1, 2, 3, 4, 5, 6, 7, 8. So right now I have a total of 10, but if you notice, my atomic number is 15, so I need 15 of them. So that's 10, and I have another one, and 1, 2, 3, 4, 5. Okay, so if you count all my electrons, I should have 15 electrons because that's what my atomic number is. Okay, and I don't have any ion symbols or anything for my neutral atom. And so that is all for our Bohr model. And then if I do the anion, it's going to look very, very similar. 2 and 2. I've got 1, 2, 3, 4, 5, 6, 7, and 8 in that one. And then here's where it changes. In the third level, notice that I've gained 3 electrons. Okay, I have a -3 charge. Okay, 3 more negatives. So instead of having 5, I'm actually going to have 8. 2, 3, 4, 5, 6, 7, and 8. And so if you count them all, I've got these 15 plus 3 more electrons. That's what the -3 stands for. Okay, for a total of 18 electrons. Okay, now on the test I do ask a question about why certain ions always form the way that they do. If you think back to the octet rule, okay, this one has 5 valence electrons, okay, 5 outer electrons. It wants to get to 8. Okay, well, what's the easiest way to get from 5 to 8? Well, that's by adding 3 electrons. Okay, and that's why phosphorus is always going to form a -3 ion, because it's always going to gain 3 because it wants to get to 8. Wants to all the time, no matter what, it wants to gain 3. Okay, I hope that is clear. And so those would be my Bohr models. Now I'm going to erase some of this stuff up here so that I can show you Lewis dot structures. Okay, so if you remember, Lewis dot structures only show the valence electrons. Okay, so if I do phosphorus like this, I put a P, and then this one has 5 valence electrons. So what I do is I do 1, 2, 3, 4, and then 5. Okay, now for the ion, technically I would have 8. So I'd go 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that's how I would make my Lewis dot structures. Notice that the Lewis structures, okay, they only show valence electrons because those are the most important. But Bohr models show all of them. Okay, and that's all you need to know for Bohr models and Lewis dot structures. Okay, the last one, kind of to explain why valence electrons and ions form the way that they do. Okay, it goes back to what I was saying about, for example, this group has 1 valence electron. This group will have 2 valence electrons. This group always has 3 valence electrons. This one has 4, this one has 5, this one has 6, this one has 7, and these ones have 8. Okay, so if I go back to why the noble gases don't bond with anything, That's because they've already satisfied the octet rule. Okay, and in helium's case, helium already satisfies the duet rule. Okay, that's why these don't bond. Okay, they don't bond because they already have full outer shells. So if you imagine this group that has 7 and is trying to get to 8 really wants 1 electron. Okay, and once we start talking about bonding, we'll figure out that this group really loves to bond with that group because this group has 1 valence electron and they want to give that 1 away to them so that they can both become stable. Okay, so lithium and fluorine, well, lithium has 1 to give, fluorine wants 1, so then they're going to bond much easier than other atoms or other elements to themselves. Okay, likewise, this group that has 6 and wants 2 to get to 8 is really going to bond with this group because they have 2 and they want to give those 2 up to become stable. Okay, I hope that clarifies some of your ions. Okay, that's why these ones form 1+ ions or 2+ ions. These ones form 3+ because they give away 3. 4 is kind of right in the middle because if you imagine I can give away 4 or I can gain 4 to get to 8. These ones form 3-. These ones form 2-, 1-, and so on. Okay, again, that'll make hopefully more sense when we talk about chemical bonding as well. I just thought I'd throw it out there to see if you guys could understand the relationship between the formation of ions and their valence electrons. Okay, other than that, that is all I have for you as far as reviewing for the unit test. Okay, make sure that you do your best on it. If you have questions, let me know. If you want to come in for office hours right before you take it so we can talk about some things, please do so. Other than that, thanks for watching.